Here's another Newton's second law example problem. Here we have three objects. Two masses, M2 and M3, are connected by a spring and are sliding on a frictionless surface. An ideal string wraps around a massless frictionless pulley and attaches a third mass to mass 2. All three masses have the same acceleration. How fast are they accelerating, and how much is the spring stretched? Now it says they have the same acceleration, but really this one is accelerating down, and these two are accelerating to the left. It just means that the size of the acceleration is the same for each one. They have the same number, but they point in different directions, but that's okay. All right, so we have three different objects, so I'm going to have three different picture equations. Let's start with what I think is the easiest one, M1. So for M1, we have the string pulling up, so I'm going to label that with T for tension. We have gravity pulling down, so I'm going to label that M1G. Because we've got three different masses, we're going to have three different gravity forces, so I want to be able to label each one differently. And those are the only two forces on M1, and so what I do is I set that equal to M1 times the acceleration, and for M1 we know the acceleration goes down, so I'm going to draw that as a downward arrow. Okay, so that's a picture equation for M1. Let's look at M2. So for M2, we again, this time we have a normal force pointing up, and I'm going to label that N2 just to be clear that it's the normal force on the second block. And that normal force is from the table. The table is pushing up on the block, and it's a normal force because the block is touching the table. Normal forces happen when your object is touching another solid object. Okay, and then we have a tension force pulling the block to the left. Now, I have intentionally labeled this tension force and this tension force with the same letter T. And the reason is we're told that this is a massless, frictionless pulley and that this is an ideal string. Well, ideal strings will have the same tension on both sides, and a massless, frictionless pulley doesn't change the tension of the string. So what that means is that the tension force pulling here and the tension force pulling here are the same. This is not Newton's third law because this is the string pulling on block 2 and this is the string pulling on block 1, and those don't follow the pattern for Newton's third law. But it's still the same force. That tension force is the same on both. And actually, we're going to have the same thing with the spring. The spring pulls forward on M3 and the spring pulls backwards on M2. If it's an ideal spring, both of those forces are going to be the same. All right, so we'll get to that in just a second. Back to block 2, we have a gravitational force, which is pulling down. I'm going to label that M2G. And we have the spring pulling to the left. I'm going to label that force of the spring. And those four forces together are going to cause this thing to accelerate to the left. So we'll label that M2, and we know the acceleration points to the left. Okay, let's look at block 3. So for block 3, we have a normal force from the table. The table's pushing up on it with a contact force, which we call the normal force. Gravity is pulling down on that. We're going to label that M3G because it's the force of gravity pulling down on M3. We know the spring is pulling it forward, or to the left, I should say. So the force of the spring is to the left. And there is no friction, so there's nothing pulling it to the right. So those three forces together should equal M3 times the acceleration. And again, we know it's accelerating to the left. Okay, now that I've got my three picture equations, each one of those can produce some mathematical equations for us. So for the first one, I'm going to make down positive. Now, why am I making down positive? Because the acceleration is down. And I always like it when my acceleration is positive. So what does that give me? That says that if I add up all of my y forces, it should equal mass times my y acceleration. So I get m1g is my positive force minus the tension is my negative force is equal to m1a. All right. And I'll go ahead and put a box around that equation because that is the equation that I got from the first picture. Now, I could say that if I add up all the x forces, I get mass times the x acceleration. But if you add up all the x forces, you get 0, and the x acceleration is 0, so you just get 0 equals 0, which isn't a very interesting equation. All right, let's move on to the second picture. And for this one, I'm going to make to the left positive and up positive. And so let's create two equations. If we add up all the x components of all the forces, we should get mass times the x component of the acceleration. So that's T minus the spring force is equal to m2a. And so that's my first equation. And if I add up all the y components of all the forces, I should get mass times the y component of the acceleration. So that's normal force 2 minus m2g is equal to, and the y component of the acceleration for this mass is 0 because it does not point up or down at all. So that's 0. Okay, and then let's look at our last equation. Again, I'm going to make to the left positive and up positive. So this is going to be my x direction, and this is going to be my y direction. So if I add up all the x components of all the forces, I should get mass 3 times the x component of the acceleration. And if I add up all the y components of all the forces, I should get mass 3 times the y component of the acceleration. So in the x direction, that tells me that the force of the spring is equal to m3a. And in the y direction, I find out that normal force number 3 is equal to, minus m3g is equal to 0. And again, I'll put boxes around those little equations because now those 5 equations are going to help us answer the problem. The problem wants us to find how fast they are accelerating and how much the spring is stretched. So let's find the acceleration first. Okay, so it turns out to find the acceleration, we're not going to need these 2 equations. So let's look at the top 3 equations. On the left, I can use this equation to say that tension is equal to m1g minus m1a. Now, I did a little bit of algebra there, but go ahead and see if you can follow that algebra and make that make sense. And on the far right side, we have the spring force is equal to m3a. So I'm going to take both of these and plug them into this middle equation. So for tension, we have m1g minus m1a. For the spring force, we have, I'm going to put in my minus sign from the equation, and for the spring force, we have m3a. And those 2 together are going to equal m2a. Now, if we're trying to solve for acceleration, what we want to do is get everything that has acceleration together on one side of the equation and everything that doesn't have acceleration together on the other side of the equation. So let's rearrange this as m1a plus m2a plus m3a equals m1g. And again, I will let you, if you want to pause a minute to check that algebra and make sure it all works, you can do that. So now the next step in our algebra is to notice that we've got a in all three terms. So we're going to pull that out. A times m1 plus m2 plus m3 equals m1g. So my acceleration is equal to m1 over m1 plus m2 plus m3 times g. So what I did is I divided both sides of the equation by the thing in parentheses. On the left, the thing in parentheses canceled, and on the right, I got m1 divided by the thing in parentheses times g. Okay, going back to the problem, we were told that m1 is 1 kilogram, m2 is 2 kilograms, and m3 is 3 kilograms. That's easy to remember. So this is 1 over 6. 1 kilogram divided by 1 plus 2 plus 3, which is 6. So this is equal to g over 6. 9.81 divided by 6 is equal to 1.635 meters per second squared. And let's just check the problem again. This problem had 2 significant digits. So since it had 2 significant digits given in the problem, I'm going to use 2 significant digits in my answer, which means that the acceleration is equal to 1.6 meters per second squared. And that means that m1 is accelerating down at 1.6 meters per second squared, and m2 and m3 are accelerating to the left at 1.6 meters per second squared. The second question is, how much is the spring stretched? Now, what I know about springs is that the force of the spring is equal to kx, where k is the spring constant of the spring, and x is how much it's stretched. So looking way back, we found out that our spring force should be equal to m3a. So that means that m3a should equal kx. So to find the stretch, I need m3a divided by k. Plugging that in, m3, of course, is 3 kilograms. K is 45 newtons per meter. So 3 kilograms times the acceleration. And for the acceleration, I'm going to plug in the full value, 1.635. I'm not plugging in 1.6 because I never plug in rounded off numbers in my calculator. So I got 3 times 1.635 divided by 45 gives a stretch of 0.109 meters, but again, 2 significant digits, so x is 0.11 meters, which is 11 centimeters, which is, a little bit more than 1/10 of a meter stick. So maybe approximately the length of your hand from your wrist to your the tip of your middle finger, roughly speaking. And 1.6 meters per second squared is significantly less than the acceleration due to gravity, which is 9.8 meters per second squared. So it's accelerating, but it's not accelerating nearly as quickly as if it was just being dropped. Okay, so there is an example problem.